Voyager 2 has made its biggest discovery yet. Something happened at Uranus in January of 1986 that no scientist could explain for almost 40 years. A single spacecraft flew past a planet no human instrument had ever touched, and in the space of a few hours it recorded a number that should not have existed. Radiation levels so extreme, so far beyond every prediction, that the people reading the data back on Earth assumed at first that something on the spacecraft had broken. Nothing had broken. What Voyager 2 had flown into was real, and for 39 years nobody could say why. That silence just ended. In February of 2026, a team of scientists at the Southwest Research Institute published findings that finally crack open one of the strangest unsolved mysteries in the history of planetary science, and the answer is stranger than the mystery itself. But to understand why this new discovery matters, you have to go back to the moment it began. Because what happened on that January day in 1986 was never just a data anomaly. It was a warning that nobody knew how to read. Voyager 2 was never supposed to still be relevant in 2026. It launched in the summer of 1977, before most of the people watching this video were born, writing a rare planetary alignment that would not repeat for another 175 years. That alignment let a single spacecraft visit Jupiter, then Saturn, then Uranus, then Neptune, using each planet's gravity to slingshot toward the next. No mission before or since has done what Voyager 2 did. It remains, to this day, the only spacecraft in human history to have flown past all 4 giant planets of the outer solar system. Every image you have ever seen of Uranus up close, every measurement of its magnetic field, every count of its moons and rings, all of it traces back to a handful of hours in January 1986, when one machine, moving at nearly 10 miles per second, got one chance only to look. And what it saw broke the model. Scientists expected Uranus to behave, more or less, like a smaller, colder version of the other giant planets. Instead, Voyager 2 found a planet tipped over on its side, spinning almost horizontally as it orbits the Sun, with a magnetic field wrenched wildly off-center from its rotational axis. But the detail that quietly troubled physicists for decades wasn't the tilt, and it wasn't the strange magnetic geometry. It was the radiation belt. Voyager's instruments detected an electron radiation belt around Uranus that was, by every comparison to other planets, impossibly intense. Read that again. A belt of high-energy radiation trapped around a planet that, according to every physical model scientists had, should not have been able to hold that much energy in the first place. For most people, that would have been a footnote. For planetary physicists, it became an open wound. Because in science, an anomaly you cannot explain is not just an inconvenience, it's a signal that your understanding of the system is incomplete. And an incomplete understanding of a planet 1.8 billion miles from Earth is not something you can simply go back and check. There was no second flyby. There was no follow-up probe. Voyager 2 flew past Uranus once, took its measurements, and kept moving. Whatever caused that anomaly happened in a window of hours, and then it was gone, buried in a single dataset that nobody had the tools to fully decode. Until now. Here is where the story stops being about the past and starts being about the present. The team at WRI didn't get new data from Uranus. There is no new spacecraft out there. What they did was something almost more unsettling. They went back into the old Voyager 2 data with decades of new knowledge that simply did not exist in 1986, and they started asking a different question. Not what is wrong with Uranus, but what if nothing is wrong with Uranus at all, and instead we caught it on the worst possible day. Think about what that means. For nearly 40 years, the assumption baked into planetary science was that the extreme radiation Voyager 2 recorded represented Uranus's normal baseline state. Every theoretical model built since 1986 had to somehow account for a planet that just runs unusually hot with radiation, all the time, for reasons nobody could isolate. But what if that assumption was wrong from the very beginning? What if the planet scientists have spent decades trying to explain was never actually behaving normally in that flyby window at all? This is where the new research gets its edge, because the team led by Dr. Robert Allen didn't approach this like an astronomer studying a distant world in isolation. They approached it like meteorologists studying a storm, space weather. That's the phrase that unlocks everything. Earth sits inside a constant stream of charged particles pouring off the sun, called the solar wind, and every so often that stream develops structures within it, dense regions of plasma and magnetic field, called co-rotating interaction regions, that slam into a planet's magnetosphere and dramatically supercharge its radiation belts. Scientists have watched this happen to Earth directly. In 2019, one of these solar wind structures hit Earth's magnetosphere and caused a massive measurable acceleration of radiation belt electrons, an event well documented by modern satellites in a way that simply wasn't possible in the 1980s. And here is the moment the entire 40-year mystery flips on its head. The SWRI team compared the wave signatures Voyager 2 recorded at Uranus in 1986 to the wave signatures recorded during that 2019 Earth event, and the two matched the same underlying pattern. High-frequency plasma waves, the strongest ever detected during Voyager 2's entire mission, present at Uranus during that flyby. In 1986, scientists believed these kinds of waves would do the opposite of what actually happens. They believed the waves would scatter energetic electrons, causing them to fall harmlessly into the planet's atmosphere and disappear. But research conducted in the decades since has proven that under the right conditions, those same waves do not scatter electrons away. They accelerate them. They inject even more energy into a planet's radiation belts, supercharging them instead of draining them. This is not chaos. This is a storm. Voyager 2 didn't discover a planet with a permanently, inexplicably intense radiation belt. According to the researchers, it almost certainly flew past Uranus during a rare, violent burst of space weather, a cosmic storm surge that happened to be washing over the planet at the precise moment a spacecraft from Earth was passing through. Out of the nearly 200 years it will take for another spacecraft to have this kind of alignment opportunity. Again, Voyager 2 arrived during what may have been one of the most electrically violent windows in that entire span. The odds of that timing, purely by chance, are almost uncomfortable to sit with. But here's where it gets worse, in the best possible way, for our understanding of the outer solar system, and worse in the sense that it exposes just how little we actually know. If a single chance encounter with one storm event was enough to produce readings that baffled scientists for 4 decades, then everything we think we know about Uranus's normal state, its baseline magnetic environment, its typical radiation levels, all of it may be built on a distorted snapshot. Imagine trying to describe the climate of an entire country based on a single afternoon, and that afternoon happened to be the worst hurricane in 100 years. That is roughly the scale of the correction planetary science may now be facing. And this is where everything changes, because the implications don't stop at Uranus. Neptune, the 8th planet, the last one Voyager 2 ever visited before it left the planets behind entirely, shares deep structural similarities with Uranus. Both are ice giants. Both have magnetic fields dramatically tilted and offset from their rotational axes in ways the other giant planets, Jupiter and Saturn, do not share. If a solar windstorm was capable of so violently distorting the radiation environment at Uranus, the same mechanism could be reshaping our understanding of Neptune's magnetosphere too, built on Voyager 2's single 1989 flyby, a dataset that has sat almost entirely unchallenged for over 3.5 decades. Dr. Allen himself pointed directly at this consequence, noting that the findings carry serious implications for similar systems, specifically naming Neptune as a system where the same kind of hidden storm distortion may be lurking in the numbers scientists have trusted for a generation. What most people are not seeing, when headlines simplify a story like this into a tidy, mystery-solved narrative, is that solving one mystery here didn't close a door, it kicked one wide open. The SWRI researchers themselves were explicit about this, understanding that a storm caused the anomaly is not the same as understanding the storm itself. Scientists still do not fully understand the exact physics, the precise sequence of events that allows these high-frequency waves to form in the first place and transfer energy into a planet's radiation belt with such devastating efficiency. The question mark hasn't been erased. It's been relocated to a deeper, more fundamental layer of the problem. And that reframes an uncomfortable truth about the outer solar system that most people never think about. Everything we believe we know about Uranus and Neptune, their magnetic fields, their radiation environments, their atmospheric chemistry, rests on data gathered during single fleeting flybys that lasted only hours decades ago, using instruments that are primitive by today's standards. No orbiter has ever circled either ice giant. No probe has ever dropped into their atmospheres. Compare that to Jupiter, which has been visited by multiple dedicated missions, orbited for years at a time by spacecraft like Galileo and Juno, studied in exhaustive, continuous detail. Compare it to Mars, crawling with rovers and ringed by orbiters. The ice giants, by contrast, remain almost a blind spot in humanity's exploration of its own solar system, understood almost entirely through data snapshots that this new research suggests may have captured worst-case, once-in-a-generation storm conditions, rather than anything resembling a stable baseline. This is where the story stops being about a single planet and becomes something bigger. Because right now, in 2026, there is no approved mission to Uranus. There is no approved mission to Neptune. Multiple concepts have been proposed over the years, ambitious names like the Uranus Orbiter and Probe, or Odinus, a twin orbiter concept meant to study both ice giants at once, or Oceanus, envisioned as an orbiter built on proven technology. Every single one of them remains, as of this year, unapproved, undeveloped, unfunded. The most detailed, most enticing new evidence in nearly 40 years, pointing toward how poorly understood these worlds actually are, has landed at a moment when there is no active spacecraft en route to either of them, and none scheduled to launch in the foreseeable future. Read that again. The single most compelling scientific argument for returning to Uranus in decades has just been published, and there is currently no mission on the books to act on it. Every answer this new research provides only sharpens the case for going back. And every improvement in our understanding only highlights how much of what we know might need to be rewritten once real, sustained data finally arrives. According to informed voices within the planetary science community, this is precisely the kind of finding that mission proposal teams will now be citing for years in every grant application, every NASA decadal survey submission, every pitch to secure funding for an ice giant mission that has been talked about, dreamed about, and shelved for over a decade. But there is another layer to this story, one that makes the timing of this discovery feel almost impossibly poignant. Because the spacecraft that captured this data, the machine at the center of this entire 40-year mystery, is still out there right now. Voyager 2 did not stop at Neptune in 1989, but it kept going. It crossed the outer boundary of the solar wind's influence, a region called the heliopause, in December of 2018, becoming only the second human-made object in history, after its twin, Voyager 1, to leave the protective bubble the sun generates around our entire solar system and enter true interstellar space. It is still transmitting. It is still, in a very real sense, alive. But it is dying, slowly, deliberately, on borrowed time that engineers have been stretching for years through increasingly difficult decisions. Voyager 2 runs on a radioisotope thermoelectric generator, a power source that converts the heat of decaying plutonium into electricity, and that power source loses roughly 4 watts of output every single year. It cannot be repaired. It cannot be refueled. There are no service missions, no second chances. 1.8 billion miles from home is not a distance you send a repair crew across. To keep the spacecraft's remaining instruments alive for as long as possible, NASA engineers have had to make a series of quiet, almost mournful decisions, switching off one instrument after another, sacrificing pieces of the spacecraft's senses one at a time so the rest of the body can keep functioning a little longer. Think about what that means for a machine that is, right now, one of only 2 human artifacts ever to touch the space, between the stars. Every year it sees less. Every year it hears less. And every year, the window in which humanity can still receive a signal from beyond our solar system's edge, from a machine older than most of the people watching this, narrows just a little further. This is the part of the story that mainstream coverage almost never sits with long enough. It's easy to treat Voyager 2 as a historical artifact, a piece of 1970s engineering that did its job decades ago and is now simply coasting through the dark as a footnote. But this new discovery proves the opposite. The data Voyager 2 collected in a matter of hours, decades ago, is still active. It is still being mined, reanalyzed, and reinterpreted using tools and knowledge that didn't exist when the numbers were first recorded. In a very real sense, Voyager 2 is still making discoveries today, not through new transmissions from the edge of interstellar space, but through the sheer depth of what it managed to capture in those brief, irreplaceable windows when it was still close enough to a planet to actually look. And that raises a question that should sit uncomfortably with anyone paying attention. If a single flyby, lasting only hours, buried inside 40-year-old data, could still be rewriting fundamental assumptions about an entire planet in the year 2026, what else is sitting inside that same data set, waiting for someone with the right tools and the right question to notice it? Uranus's rings, its moons, its atmosphere. Every one of those data sets was gathered during the exact same storm-distorted flyby window. Nobody has systematically gone back and asked which other measurements might have been skewed by the same violent space weather event that supercharged the radiation belts. The Uranus that Voyager 2 photographed and measured in January 1986 might, in more ways than scientists currently appreciate, be a planet caught mid-storm, not a planet caught at rest. The uncomfortable truth underneath all of this is that humanity's entire picture of 2 full planets in our own solar system, worlds larger than Earth, worlds that may hold clues about the most common type of planet in the entire galaxy, since ice giants appear to be one of the most frequent planetary categories discovered around other stars, rests on data from 2 brief flybys that new research now suggests may have caught both worlds during freak, statistically rare conditions. Every exoplanet scientist studying Neptune-sized and Uranus-sized worlds orbiting distant stars is, whether they realize it or not, building their models on a foundation that may need significant revision. This isn't just a story about one planet in our backyard. It's a story about the baseline assumptions underpinning how astronomers interpret an enormous category of worlds across the entire galaxy. So where does that leave us? A discovery that took nearly 40 years to arrive, made not by a new mission, not by a new spacecraft, but by scientists finally catching up to the physics needed to understand what an aging probe recorded during a few violent, chaotic hours in 1986. A mystery solved, and in the same breath, a much larger one exposed. A spacecraft still transmitting from beyond the edge of the solar system, its power fading year by year, its senses being deliberately dimmed one instrument at a time to buy a little more borrowed time, even as the data it gathered decades ago continues to force scientists to rewrite what they thought they understood. And two entire planets, Uranus and Neptune, sitting in the dark at the edge of our solar system, almost entirely unexplored, with no funded mission currently planned to go back and check whether the storm-distorted snapshot from the 1980s bears any real resemblance to what is actually out there today. The real story here was never just about a radiation belt. It's about how much of what we call scientific knowledge is built on fragments, single moments captured by machines that only ever got one chance to look, and how those fragments can sit quietly for decades before someone finally asks the right question. Voyager 2 is still out there right now, still moving, still transmitting, carrying data. Humanity has not finished decoding and may not finish decoding for years, possibly decades, after its power finally runs out for good. Somewhere in the numbers it already sent home, numbers that have been sitting in archives since before most of the world had ever touched a computer. There may be more storms waiting to be found, more assumptions waiting to be overturned, more evidence that the solar system we think we know is far stranger, far more volatile, and far less understood than anyone has been willing to admit. And when Voyager 2's last instrument finally goes silent, whenever that day comes, humanity will be left with exactly what it has right now. No new data, no second flyby, just the archive, and the people patient enough to keep looking at it. The question nobody in this story has really answered yet is not what Voyager 2 found in 1986. It's what else is still hiding in that data, waiting for the next person to ask the right question before the chance to ask it at all quietly disappears forever.